Hello everyone. Welcome back to class. Let me ask you something. Have you ever noticed how quickly your cold coffee warms up in the sun compared to how slowly your hot tea cools down in winter? That speed of change in temperature is exactly what we study with derivatives. Surprising, right? Whether it's your battery percentage dropping 5% in 2 minutes or your car accelerating from 0 to 60 in 10 seconds, derivatives explain it all. So remember, derivatives aren't just slopes of graphs. They are the mathematics of change everywhere in life. Now, where do derivatives sneak into our daily life? Let's explore. First, rates of change. Like petrol consumption, liters per kilometer, which is dy by dx. Second, tangents and normals. Imagine a bicycle tire touching the road. The line of touch is the tangent, and the line perpendicular to it is the normal. Both come from derivatives. Third, monotonicity. Using derivatives, we decide if a company's profit graph is going up or down. Fourth, turning points. Just like hills and valleys on a trek, maxima and minima appear where slope becomes zero. And fifth, approximations. Want to find square root of 100.5 without a calculator? Differentials make it easy. So, whenever you hear the words maximize or optimize, smile because derivatives are behind it. Let's zoom in. In physics, if s is distance, then velocity equals ds by dt, which is rate of change of distance with respect to time. And if velocity itself changes, acceleration equals dv by dt. For a function y equals f of x, the rate of change is dy by dx. At a point x0, we write dy by dx evaluated at x equals x0. Sometimes both x and y depend on time. For example, radius of a balloon and its volume both grow with time. In that case, by the chain rule, dy by dx equals dy by dt divided by dx by dt, provided dx by dt is not equal to 0. So when you see ripples expanding in water after dropping a pebble, that's derivatives in action. Now geometry time. Suppose we have curve y equals f of x and a point x0, y0. The slope of tangent there is m equals f dash of x0. So its equation is y minus y0 equals f dash of x0 multiplied by bracket x minus x0 bracket close. The normal is simply perpendicular to tangent. Its slope is minus 1 divided by f dash of x0. Its equation is y minus y0 equals minus 1 over f dash of x0 multiplied by bracket x minus x0 bracket close. Think of a skateboard sliding along a curved ramp. The board's direction is tangent, the sudden break line is normal. Functions can rise like mountains or dip like valleys. To detect these, we check critical points where derivative equals 0. By the first derivative test, if slope changes from positive to negative, it's a local maximum. If slope changes from negative to positive, it's a local minimum. By the second derivative test, if f double dash of c is less than 0, then maximum at c. If f double dash of c is greater than 0, then minimum at c. Think like a hiker. When the climb turns into a descent, you've reached the peak. When descent turns into climb, you've reached the valley. Let's solve. Area of a circle is a equals pi r squared. Differentiate with respect to r, dA by dr equals to pi r. Now take radius r equals 5. Substitute dA by dr equals to pi into 5 equals 10 pi. So, when the radius is 5 centimeters, the area is increasing at 10 pi square centimeters per second. A small change in radius creates a big change in area, just like how a small increase in pizza size makes it feed to extra friends. Another gem, approximations. For small delta x, f of x plus delta x approximately equals f of x plus f dash of x times delta x. In words, delta y is approximately equal to slope times delta x. It's like saying, if you walk a very small step on a curve, the tangent line can predict your height change. Engineers use it to estimate pressure changes, economists use it to predict profit variation, and scientists use it to calculate error margins. Derivatives here act as fast mental calculators, quick, simple, and surprisingly accurate. So to wrap up, derivatives are our best friends for understanding change. We studied their applications, rates of change, tangents and normals, finding increasing or decreasing intervals, maxima and minima, and quick approximations. Everywhere, physics, economics, biology, engineering, derivatives quietly power the answers. They are the mathematics of motion, growth, and optimization. In our next session, we'll explore rate of change of quantities with exciting real-world problems like expanding balloons, sliding ladders, and even cost-revenue analysis. Stay tuned because this is where calculus truly comes alive.